Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and privilege to be serving you today, as it is every day here in my virtual classroom with fractal zooming in the background. I sure love these ones. I don't even know how people make them, but I sure love to check them out. You'll love to check it out as well as you check out some math with me. I have integrated Math 1 material here, kind of going into the final stretch of our fall semester as we solve systems of linear equations. We actually go into, if you're curious, we're going into the next semester, starting off with solving systems of equations word problems and solving graphing inequalities and solving systems of inequalities with word problems as well, all in a linear realm only. Again, this is an integrated Math 1, kind of an Algebra 1 basis here. So coming out of the break, you'll be seeing a couple review videos, I'm sure, on those, at least one of them, because this one for them is a practice test. And for you, it can be any sort of review if you'd like to as well. Take a look, go ahead and go to the description section down below and find a link for the attachment for the PDF that I'm going to show you here. This will kind of just essentially be the PDF in and of itself. I don't break up per problem on each page here. This is literally a per page thing. I'll scroll down the page and show you as much space as you would have on the same paper if you print it out or so. And also, of course, if you look down in the description section below, you should see timestamps for each corresponding problem. Without further ado, guys, let's go ahead and get into it because, oh, one more thing actually I want to say about this. I am going to go over this almost as more of a strategy guide than a solution guide. And I mean, it'll show solutions. What I mean by that is normally when I do a solution guide, I want to kind of reteach the material. Here, I'm going to kind of more so do the problems as if you have already learned it before. Now, I'll explain what I'm doing, but I'm not going to just go back and forth and literally reteach every little aspect. What you see goes. So the strategies are my preferences and how I do it when I use the substitution method or elimination method, or if I graph, whether I graph out of slope-intercept form or standard form. All right, good old quick 2-minute intro there. Let's go ahead and get started here. And if you want to write your name and date, that is great. Number 1, determine the number of solutions for each system of equations in A through E. Circle the appropriate answer. So each part is its own question. So part A, here's a graph for 2 lines within a system of equations. They're asking us how many solutions would there be. So this is me. I'm not going to teach so much here, but as far as saying they never intersect, that means there are 0 solutions. If they never intersect, then there are not any solutions to that. Okay. Now part B is in equation form, y equals 2x plus 4 and y equals 2x minus 5. Without actually solving this system, what you can look at here, whether you and without graphing it, and without actually doing the substitution method or anything, you can look at these as both slope-intercept form. And what we can see in slope-intercept form is they have the same slope. Y equals 2x plus 4 and y equals 2x minus 5. And same slope would either mean that they're right on top of each other or they're apart from each other. It all depends on, are they the same line? Plus 4 means this thing starts with the y-intercept of 4. This one is a y-intercept of negative 5. They are in 2 different places as they fall. This might be that graph for this thing. This might be y equals 2x plus 4 and y equals 2x minus 5. I don't really know. What I do know is these lines are parallel. And these parallel lines do not intersect either. There are 0 solutions to this guy as well. Part C, y equals 3x minus 2 and y equals 2x plus 1. Again, they're not asking for us to actually solve it. They don't want to know what the actual x comma y coordinate pair is. So I don't need to actually solve this to answer this question, how many solutions there are. If we think of this like a graph, as these are both in slope-intercept form, because they have different slopes, regardless of y-intercept, because they have different slopes, one will cross the other at some point, and then it would pass it. But it only hits it just that one time. So if it only hits it once, there will only be one solution to this. I don't know what the solution numbers are right now off the top of my head. I don't know if the solutions are integers or not. I mean, I assume they are, given the nature of these. But what I do know is that they only cross once. There's only one location where they do hit, and that's all we need to know. All right, part D, we have 2 lines right here, and of course the number of solutions is the number of times that these 2 things intersect. These are the x and y axis, just so you're certain of that, and then this is where these 2 unique lines cross at one point. I don't know what the point is, but I do know that it's only hitting once. That's one solution. And lastly, part E, you probably can't tell. It only looks like one line, but even as I'm looking at it right now here, I have, this is kind of bolder, like thicker, probably because what you're seeing is one line right on top of the other. And what's happening is they're intersecting everywhere at every point in time. this is so many solutions that we don't even state what any of them are. We just say there are infinitely many solutions or an infinite number of solutions or what have you. And that would be number 1. Number 2, the graph of a system of linear equations is shown below. What is the solution of the system right here? So there is only one solution to this thing, and this is multiple choice, by the way, but without looking at multiple choice, we should actually be able to determine this answer as well. So in this multiple choice section, though, the options are 0, 3, 0, 6, 2, 4, and 6, 0. Okay, so let's see the 4 points that they gave us. Here's 0, 3. Here's 0, 6. Here is 2, 4. And here's 6, 0. All of them do cross something at each of those moments, but you want to make sure that you are referring to the system solutions and not just an x or y intercept. Case in point, this line here is the y-axis and is not the equation, is not the line of one of my equations here. So this 0, 6, and this 0, 3, those are just y-intercepts. This 6, 0 is just an x-intercept of some sort. This one right here, ding, ding. 2, 4 is the point of intersection. I'm spending more time on this problem than I need to. But just to make sure, if you understand through multiple choice, why they even had those options available, because they're hitting something. But intercepts are not necessarily solutions. Solutions are where your two lines intersect, and these two intersect at this one point. 2, 4, the answer is C. Okay, number 3. Does the following system of equations have a solution of 3, -8? Justify your answer using any means necessary. Well, there are several different means that we could be using in this guy. I'll show you every single set. Well, let's see if I can do this one. No, it doesn't fit at -8. I'm not going to show you it by graphing. Let me show you the way that you probably should be approaching this problem here. When you have a solution present and available to you, you don't need to necessarily solve the system and see if it matches what you have. What you could do is use these answers of 3 for x and -8 for y and substitute them into both equations. So I'm going to first try and do that. I'm going to take this solution set and I'm going to do 2, top equation. This is 2 times 3 plus y value of -8 equals -2. 2 times 3 is 6. 6 plus -8 is 6 minus 8. And does 6 minus 8 equal -2? You betcha, it sure does. -2 equals -2. That top equation surely checks out, and it lets us say that, all right, 3 -8 is at least a solution to the top equation. We need to make sure that it is a solution to both equations. That's what makes it a solution of the system. And of course, that means that that's where these 2 points intersect. Unless they're the exact same line, which I'll go and show you later that they're not. Here's the other one. -8 minus y equals 5. That is -8, -x. That's -3 minus -8 equals 5. -3 minus the negative is plus 8 equals 5. And -3 plus 8 is 5. 5 equals 5. That checks out as well. So both of these check out. So the answer to this unequivocally is yes. It is yes. Okay. Yes, indeed it is. Now, this is the way that I recommend doing it for several reasons. What if there was only really one equation we were talking about right here and just asked if that was the solution to it? How would you figure out if that was a solution without trying to say, there's no system to solve for this time. There's an infinite number of solutions on x and y. That's another point I'm going to make on this. That's another, there's an infinite number of solutions on x and y. When x is 1, y is a different number. And when x is, so you could graph it, but unless you have the graph stuff available to you, which I do not, and if this is way out of window range, that's why I was going to graph here. I was going to use -8 right here, but it was out of window range, so I said, never mind, I won't graph them. But I could. But that being said, this is the way that I'd recommend you doing it, because if it was this kind of problem right here, just one equation, that's what you should do. Now, if it's both equations, you might say, well, Mr. Robinson, I could solve the system. It's actually pretty fast to solve, and I'm not going to take this away from you. It is pretty fast to solve. If I use the elimination method here and I add down these lists right now, I would get 2x plus -x, 2x minus x is 1x, and y minus y is 0. These are additive inverses that eliminate immediately, and I do get x equals 3. That was really fast. And then substituting that 3 in for x, maybe for the top equation. And this is the stuff I'm going to do later anyway. 6 plus y is -2, and y equals -8. So I will get 3, negative 8, which seems like that does match 3 for x, negative 8 for y. That's the way you can do it. One reason I wouldn't do that is because, well, generally, it would generally be slower. This one was already set up for you to do that, and maybe I set up this problem easily enough so you could use this if you wanted to. A good, easy beginning, kind of to your test, if you will. But here's the thing. What if this one did have a negative 2x? Let me erase the little part right here. What if I had a negative 2x right here? And what if, to humor me here, what if this was a negative 5 right here? When I add down these lists, guess what? We eliminate, and we eliminate, and we get 0 equals 0. Is there something wrong with that answer? Not necessarily. In fact, a 0 equals 0 would actually mean there's an infinite number of solutions. But that's the thing. Does infinite number of solutions means it hits every x, y value in the world? No, it just means it hits all the x, y values that are on the same lines together because these are, in fact, the same lines now. Does that mean it hits 3, negative 8? We're still not sure. We would have had to substitute 3 for x and negative 8 for y into either equation to figure it out. In this case, I guess it wouldn't have worked because I changed the equations to not make it so. But the point is, it's best to substitute these in just in case something like that arises anyway. You could have an infinite number of solutions case there. Now, if you did have a no solution case when you did that, well, then I suppose that means that, no, the solution wouldn't have that as a system of equations because they don't have any solution as a system, system of equations. Sorry, I'm kind of talking over my words. Anyway, so you see how I'm talking more about strategy right now? I'm not talking about this is how you use the elimination method. I'm saying this is how the elimination method can be used or not. Do this stuff. I hope that makes sense. Okay, number 4. And by the way, this front page, guys, the next page after this, it asks you to solve systems of equations. We're going to have like 6 of them in a row, and then we're going to graph some and stuff like that. So these are intro problems before we start doing the methods themselves. That's kind of why this first problem also wasn't really method-based. I would really much prefer doing that. Okay, number 4. Julio wants to solve the below system shown using the substitution method. Which is the best way for him to begin? Okay. Now, before we read the options, keep in mind, think about what substitution method means here. Let's get a variable by itself, make it say x equals blank or y equals blank in one of the 2 equations, and then we can plug in that expression into the other equation. Okay. Some of them will be easier than others based on getting fractions or not. Maybe there's more than one good answer here, but let's look at the options now and see which one is best for substitution. A, add 4x to both sides and negative 4x plus 7y equals 12, then divide every term by 7 to isolate y, and replace that expression for y in the other original equation. That's a lot to read, so let's see what they're asking you to do. Negative 4x plus 7y equals 12. That's the bottom equation on this thing. They're stating, hey, should we do this? Let's add 4x to both sides, and we get 7y equals 4x plus 12. And then we divide everything by 7, every term, and then we get y equals 4/7 x plus 12/7. And replace this right here in for y in the other equation. Now, is there anything wrong with what's asked here? No. Everything here was done correctly, including what I did, including what it asks you to do. It's done correctly. Is it the smartest play? We should probably see that at least this was substitution method. This is actually using substitution, isolating y, and plugging it in here to solve for x. But there are fractions, so maybe there is a better option. We'll take a look and see. So A is in question. A is in question. Maybe. At least it's substitution. At least it's a candidate. B, multiply each term in x minus 12y equals 2 by 4, then add it to the other original equation to cancel the x terms. So what that's asking you to do here is to multiply everything here by 4, and we get 4x minus 48y equals 8. And then here we have negative 4x plus 7y equals 12, where we add combined like terms. And what that does is that eliminates the x's, and it allows you to practically solve for y. Again, there's nothing wrong with what's being stated here. This is a good way to eliminate the variable, but this is not substitution method. This is elimination method. Julio wants to solve using substitution method. Maybe he's forced to, maybe he wants to practice it, I don't know. But he wants to solve using substitution method. So to satisfy his every whim, this is elimination method here. As much as this would work, it's not substitution method. B is not the answer. If they ask for elimination method, yeah, this would probably be fine. It probably is the best approach as well. It's the easiest way to get to eliminate a variable. C, add 12y to both sides in x minus 12y equals 2 to isolate x, then replace that expression for x in the other original equation. So in x minus 12y equals 2, if I add 12y to both sides right here, and I'm sorry I didn't write the add 4x to both sides in that one, but if I add 12y to both sides here, I get x equals 12y plus 2, and that isolated x, and then I would take that, keep the blue, take that and substitute it in for x in the other equation. I guess to solve for y. Okay, is it substitution method? Yes. Was it relatively clean? I would say so. It only took me actually one step. Notice how this one that I wrote in green, it took 2 steps. I had to first isolate the term and then fully isolate the variable. So this one only took 1 step, and there are no fractions. This looks like a very, very viable candidate. In fact, when it comes to having one in question here, so far it seems like this is correct. It seems like part C is the answer. I would move this in question thing. A, I've now ruled out. I don't think A is easier than C, which is the best way for Julio to begin. Not with fractions, not with 2 steps it takes to get there. This one, 1 step and no fractions, I'd say would be a more viable candidate. So C looks really good. Let's look at D. The system of equations has no solution, so Julio should not do anything. Whoopsie. All right. Let's rule this out in 2 ways. Number 1, I believe the system of equations does have a solution. Now, does it have an integer solution? I'm not really thinking so. When I look back at this, the elimination method one right here, notice how the x's canceled, but the y's don't look like they will cancel. And also notice how it looks like this number will be a lot bigger than this number here. And when I divide, I don't think it's going to be a clean looking answer. They're not asking you to solve this. They're asking you which way would he begin to solve a really hard answer, a really hard question, I guess. But I don't think there would be, but the y's didn't cancel. There might not be an integer solution, but y's didn't cancel. And if y's didn't cancel, that means there is at least one solution. There is a solution. I don't know what it is. So that's one way to rule this out. The other way to rule this out is even if there wasn't a solution, you got to do something to be able to get to that stage. So you got to find a way to cancel your variables. When it says Julio should not do anything, even if it has no solution, Julio should be doing something to get to that stage. He has to find a way if the y's could cancel as well alongside that. So it's definitely not D. So the answer here is C. Final answer C. And I am going slowly through this to kind of talk strategy. Remember, this is still strategy. This is what you would try and look to do to kind of answer questions that you have based on the parameters involved here. Just how you can think about these. Okay. Whoops. Okay. 1 sec. Give me 1 sec. I'm going to pause this video. 1 sec. This is for a tutoring thing. Okay. Sorry about that. It's kind of a... No, I'm not going to explain it. Okay. Next page. I don't know if I showed you, but we were just on this page here. And let's go to the next page. Numbers 5 through 10. We'll solve systems of equations using any algebraic method. If it seems like it's easier to just really do one and to completely avoid the other, I probably will. On number 5, because a variable is already by itself, this isn't already yet primed for elimination, but it is for substitution. I have y by itself, y equals 3x minus 5. I'm going to go with that form right here. I'm going to take 3x minus 5, and I'm going to substitute it for y in the other equation, because y equals it, that goes to y. I said I wouldn't teach this very much, so I won't. So in substituting for y here, I will now have the bottom equation rewritten as 8x plus 3x minus 5 equals negative 16. Now you want to get in the habit of using parentheses around the substitution. It will not affect anything here. In fact, I'm going to write the next step without the parentheses at all. But it would affect it if there was a number in front or a minus in front or something like that, as it would distribute into those terms. So just get in that habit, and also it does show what I did substitute. It makes sure that I didn't leave anything out. That went straight in for y. So I get to combine like terms here. I'm going to add 8x and 3x and get 11x. If I add 5 to both sides, plus 5, this goes away. Negative 16 plus 5 is negative 11. And if I divide both sides by 11, positive 11, negative 11 divided by positive 11 is negative 1. So I get an x value of negative 1 here. Pretty spiffy. Now I need to go ahead and solve for y, given what I have here. I have x equals negative 1. What's the y value? It's best to substitute it in the equation that already has y by itself. This one. So I can do y equals 3 times x, my negative 1, minus 5. And that is negative 3 minus 5, which is negative 8. So my final solution, remember, you have to write these as an ordered pair. My final solution here is negative 1, comma, negative 8. There it is. So the bottom part, that's the final answer. I don't know if I should, I guess I should box it, because otherwise you might look at the other boxes and ignore what I wrote here. That's where these two would intersect. Number 6. Now this one does kind of seem a little more like it's ready for elimination, doesn't it? If only the two y's, at least they're the same number. If only one of these was a negative 2y. I know some people go by subtracting outright. I'm going to try and avoid saying that. What I'll do instead, let's take maybe the top equation and multiply by negative 1. Now you can multiply the bottom equation by negative 1 as well, but what I'm recognizing here is the 7x is smaller than 8x and the 24 is smaller than 30. I'd rather get positive results if I can here. That's just a strategy thing. So if I can handle that, I definitely will. So I now have, instead of this top equation right here, which I'm going to hide, now I have negative 7x minus 2y equals negative 24 as everything multiplied by negative 1. So now that I can do that, I can add 8x with negative 7x. That becomes a positive 1x. And 2y minus 2y cancels out here, and that will equal 30 minus 24, which is 6. So x equals 6. What does y equal? I have several different equations I can use to decide to solve for y right here, including this original top one. It's really your call. I'm going to go ahead, let's just go ahead and use the top equation just to show that, hey, I can, anything like that. So I'm going to substitute 6 for x here, and I get 7 times 6 plus 2y equals 24. And that's 42 plus 2y equals 24. Subtract 42 from both sides here. I think that's negative 18. It better be. Divided by 2, I get y equals negative 9. So if I did everything right, and I'm going to do this with substitution as well. If I did everything right, the final answer should be 6 for x, negative 9 for y is the ordered pair 6, comma, negative 9. Okay. Now, I will do this problem with substitution method. There are problems where I'm more willing to do substitution than elimination as long as there's no fraction involved. And I'm more willing to do elimination than substitution if there is a fraction involved. But right here, I can look at this bottom equation. See, if you look at all 4 variables and you say, is there a variable I could get by itself and get no fractions by getting it by itself? The answer is, yeah, there's only one. It's this y right here. If I get this y by itself, I could subtract 8x from both sides, and I can divide everything by 2. All these numbers can divide by 2. 2y divided by 2 is 1y. Negative 8x divided by 2 is negative 4x. And 30 divided by 2 is 15. So I've gotten y by itself here, and y equals negative 4x plus 15. I can take this expression here and substitute it in for y in this top original equation that I had. Remember, assume I have nothing else right now. And because I got the bottom equation by itself on y, now I got to substitute in the top equation. So in that top equation here, it'll now say 7x plus 2 times, here's my y, equals 24. And I distribute the 2 here into negative 4. Let me, that should be a minus now. I distribute 2 into negative 4x, that gives me negative 8x. I distribute 2 into 15, that gives me 30. And that gives me 24 there. 7x minus 8x is negative 1x. Subtract 30 over here. 24 minus 30 is negative 6. Negative x equals negative 6, so positive x equals positive 6. There's that answer. And I can then substitute x in for 6 into, I can use this equation. Here's a pretty nice one right there. And that'll become y equals negative 4 times 6 plus 15. which is negative 24 plus 15, which is, it looks like, again, negative 9. So it looks like I did get the right answer. Whoops, my face is in the way. It looks like my face is in the way. It looks like my answer before did seem to work out. 6 comma negative 9 right there. Was elimination easier in that problem? I'd say so. I do like the concept of getting a variable by itself so I can substitute my variable into my other variable that I found into there pretty fast and briskly. But this wasn't too much of a hassle either, I guess. With a lot of positives involved, the elimination method was pretty fine and nice. Sometimes it just depends on what you have going for you. Like, take number 7, for example, which is the next one we're going to do. On number 7, I don't feel like doing substitution method here. Really seems like a good idea. No matter what, if I try and get any one variable by itself, no matter what, I will always be left with some sort of fraction somewhere. So I would rather instead stick with elimination. And to be honest, with elimination, this one is already primed and ready, kind of to do some elimination here. The top equation, and there are 2 different ways I can do this. A lot of people say multiply the bottom equation by 2, so you can eliminate maybe the x's. And I'm fine with that. But the top equation you could divide everything by 2. Division also works. I'll probably refrain. If I don't think my students are going to be doing that, and it's not necessarily helpful for them to look for it, I think I'll just multiply anyway. So let's take that bottom equation, guys. Let's multiply everything by 2 on the bottom. And now I'm going to get a new equation that says negative 6x plus 4y equals 12 right there. So let me kind of get rid of this middle equation because I'm going to add the top with the bottom to eliminate the x's here. And I get 6x minus 6x, which is 0. Those eliminate there. So now we get to combine negative 4y plus 4y, and oh, those eliminate, and those are also 0. So there's nothing on this side. Well, there's a 0 on this side. And that means this is either going to be a no solution or infinite number of solutions when they all cancel. The equals goes down, and I have negative 12 plus 12. Those go away as well. That should be red. Those go away as well. And that gives me 0. 0 equals 0. What does that mean, Mr. Glasses Guy? What does 0 equals 0 mean? Well, 0 equals 0 means there is an infinite number of solutions. There are infinitely, I think the thing said infinitely many before. Infinitely many solutions. Not much room to write on this thing. What are the solutions? I'm not willing to name them all, but they are all solutions along either equation. Right here. These were both kind of the same equation. Even though they don't look it from the beginning, they do both hold the same kind of, same kind of principles within. When I plug in this for x, I'll get that for y in either equation. Okay. So elimination method there was fine. Don't draw a smiley face guy with that. All right, number 8. Negative 4x plus 9y equals 9, and x minus 3y equals negative 6. Let me start with substitution method this time, not because I think it's easier. In fact, I don't. I would recommend elimination method. I want to save that other one for you. I want you to at least see that this is still feasible. The only variable I can really get by itself easily is this x right here and have no fractions. It takes one step. I just got to add 3y to both sides. So I'll get x equals 3y minus 6. I'm going to substitute 3y minus 6 in for x in the top equation. So in this top equation, I will now rewrite it as negative 4 times this x, notice the parentheses here, of course, plus 9y equals 9. And negative 4 distributes into both of these. You get a negative 12y, and negative 4 times negative 6 is positive 24. By the way, you might be forced to solve using a method based on what your teacher asks of you. I'm kind of letting my students decide which ones they want to do. And believe it or not, there's some students who prefer substitution almost every time out. Negative 12y plus 9y is negative 3y. If I subtract 24 over to the other side, 9 minus 24 is negative 15. So negative 3y is negative 15. Divide by negative 3, I get y equals 5. If I now take 5 and substitute it into this equation where x is, I'll get x equals 3 times 5 minus 6. So that's 15 minus 6, which is 9. So I'm going to get the final solution set. That's 9 for x and 5 for y. That's 9 comma 5. 9 comma 5. Now I will do elimination method. Sometimes I don't trust my answer. Not because I actually think I did something wrong. I just want to, check it. I don't know. I haven't done this before, so I just want to check it. there are two different ways that I can do elimination on this. Let me kind of write. I have a lot of space over here because I didn't do anything else on here. Negative 4x plus 9y equals 9, and x minus 3y equals negative 6. Now, this is not a way that you would generally do elimination method, but let me kind of show you this alternative because either variable is really quick to eliminate in my eyes here. So I'm going to do this two different ways, and I'm going to erase the other way after I show it, so I hope you're okay with that. One way is I can eliminate x first to solve for y. If I multiply the whole bottom equation by 4 right here, and if I multiply it by 4, I'll get negative 4x minus 12y equals negative 24 here. And then I can cancel. Oh, I'm sorry. It's a positive 4x. I don't know why I said negative. Oh, what did I do? Oh, no. Okay, yeah, just positive 4x. I'm sorry. I don't know. I was like, why did I make all these negative? Because those are negative. Okay, positive 4x minus 12y equals negative 24. And I can eliminate negative 4x with positive 4x. 9y minus 12y is negative 3y, and 9 minus 24 is negative 15. So I'm back where I was with this guy, where I'll get y equals 5. Okay, so I still trust my answer of y equals 5. Now, what you would normally do is you would take the 5 and substitute it in for one of the y's here to then solve for x. You know what you could also do, which again, it's normally not recommended. This one isn't bad though, because eliminating x doesn't take much either. It does maybe take erasing everything though, which might be a problem for you. I could multiply the bottom equation by a 3 as well. And what does that do? That gives me 3x minus 9y equals negative 18. What this does is this lets me solve for x by eliminating y here. Check this out. 9y minus 9y is 0. Those go away. Now I get negative 4x plus 3x. That's negative x. 9 minus 18 is negative 9. Negative x is negative 9, so x is positive 9. That's that answer. If you remember, I did get y equals 5, and then I got x equals 9, and I get 9 comma 5. So listen, the elimination method, which is kind of an interesting way of calling it, because in elimination method, you technically only eliminate one of the variables, and then you use that solution to substitute it into an equation. It's actually substitution, kind of, after that. But the elimination method, so to speak, is just to solve for one of the variables. The other one is, taking place with a solution. It's not even really substitution method either. But here I used elimination method doubly so. I did it for both variables because it was kind of clean to do on both of them. And not many problems have that luxury of just nicely multiplying just by some number there, making that happen. So anyway, that one cleaned up for us. That's good to go. I'm going to go ahead and move on. Let's look at problem number 9. Negative 5x plus y equals negative 3. 3x minus 8y equals 24. I'm going to do substitution and elimination. This time I'll start with elimination here. Negative 5x plus y is negative 3. It looks like, what can I multiply by where to eliminate what? I think eliminating x's would be harder. I can't multiply 3x by an integer to get positive 5x to eliminate those. But the bottom equation here, I can eliminate the y's if I make this a positive 8y. So if I multiply the whole top equation here by 8, I can rewrite it down below here as negative 40x plus 8y equals negative 24. So notice negative 24 and positive 24. This time the constants cancel, which is kind of interesting. I haven't seen that really yet with you guys, have I? Let me make that red. So I have negative 37x equals 24 minus 24 is 0. Divide both sides by 37. That is x equals 0. Don't overcomplicate that one. That's just 0. It almost doesn't matter what you had on this side as long as you know the x's didn't cancel there. So I get 0 for x. Now I must solve for y. I can substitute this into any equation. I'm really going to choose that top one here. Check this out. Let me rewrite the top one and show you what I'm talking about, which makes this really easy. If x is 0, what's negative 5 times 0? Well, it's 0. So what happens is this term kind of just goes away when I substitute 0 for x, and you're left with y equals. I get y equals negative 3. That's my answer. So I expect my final solution here to be 0, comma, negative 3 right there. So that one cleaned up pretty well. That was pretty good there. I'll use substitution method as well. Show you that one. Hopefully you can see me sneak this one right through. I think getting that top y by itself is quite the easiest thing. Add 5x over to both sides. I'll get y equals 5x minus 3. And now in substituting 5x minus 3 in for y in the bottom equation, we'll see here that becomes 3x minus 8 times that 5x minus 3 equals 24. I think most people are seeing that substitution method, when it's not already set up, can be a little more laborious. And I'm fine working with it, but I'm also fine working with the other one here. 3x minus 40x is our negative 37x. 24 subtracted over to the other side, we get 0, and of course you get that x equals 0. The good news here is, which it doesn't seem to really matter as much here, if I substitute 0 into this x right here, immediately you also see the negative 3, because 5 times 0 is 0, so y equals negative 3. So we still get the same answers. Because it was 0 either way, it seemed like it was really easy, even in elimination method, that y was by itself. Just so happens elimination method was probably better there. So I do hope that you're kind of watching my problems through instead of just pausing at the end and see what the answer is, because you're probably not going to be able to follow what the heck it is that I did here on these problems. All right, number 10, solve algebraically y equals negative 3x plus 1 and 9x plus 3y equals 6. Again, because a variable's already by itself, I think it probably just makes more sense to substitute. Let me show you something else here that could really help you, though. You don't have to do, most people wouldn't do this, but I could divide everything in this equation here by a 3. And the reason I'm bringing that up is because sometimes smaller numbers are just better to work with. When I substitute in for y, now I don't have to distribute anymore. I think that helps me as well. Now, would have you known to do that? Are you checking against it to do that as well? Maybe not. So I think for all intents and purposes, maybe I won't actually go about it this way. What I'm saying, though, is when I substitute, I can put this in place of y in that equation and all should be good. So thinking that maybe, because it's a strategy guide, I don't want to talk about that. But that being said, I'll use the original one just like it is here. And let's substitute negative 3x plus 1 in for y right there. So I'll get 9x plus 3 times negative 3x plus 1 equals 6. 9x minus 9x, 3 times negative 3x, so minus 9x, and 3 times 1 is 3, plus 3 equals 6. Combine like terms, 9x minus 9x is 0. Oh, okay. And I got 3 equals 6. What does that mean? Well, I didn't do any math wrong. What this tells me right here is that no matter what I substitute for x and y, my bottom and top equations will never have the same solution together. So there's no solution to the system. And that's how we say that. We end up saying no solution. No solution. So if variables cancel and left side equals right side, and I did the math right. If variables cancel and left side equals right side, there's no solution to that. All right, let's go ahead and move on forward. 2 problems where we have to solve by graphing. For numbers 11 and 12, solve each system of equations by graphing. Write both final solutions as an ordered pair x, y. I think when I wrote this, I knew there wouldn't be any no solutions or anything like that. So I just said, make sure you write the point of intersection and don't just draw it. Make sure you state where it is. All right, in number 11, I have 2 equations both in slope-intercept form here. Y equals 3 halves x minus 7 and y equals negative x plus 3. I'll do the this one here in blue and the bottom one here in green so you know which one's which. I'll kind of just graph them, but the slope of 3 halves, up 3 over 2, starting from negative 7 on the y-axis. So my y-intercept here is 0, negative 7. And I will do a rise 3, run 2, over and over and over again. And it's really good if you hit as many points as you can because you don't know where this one is going to intersect with the other equation. By the way, I can go down 3 and left 2 as well and still fit a point. I don't know yet where it's going to intersect, and I want to make sure that they intersect at the place that they're supposed to. So although a ruler helps, it does help even more that you actually do draw as many points as you can and just fit the line through there for precision. That's pretty good. Okay, the next one in green here. Now this slope here, just so you know, is a negative 1 or a negative 1 over 1. So I will fall 1 and run 1 to the right, starting from 3 on the y-axis, 0, 3. So I'm going to do down 1 over 1 here, down 1 over 1, etc., and keep going. And it looks like that's going to be my point of intersection of these two. But just to kind of keep, as I ask my students to do, plot as many points as you can fit, just because. Up 1, left 1 also counts. I know this becomes a little tedious, a little cumbersome, but you know what? Deal with it. It's okay. I lost 15 seconds of my life. It's okay. I had better things to do. It's okay. All right, what's the point of intersection here, though? where are these two things intersecting right here? That is the point 4 for x, negative 1 for y, 4 comma negative 1. And I'm not going to double check that. That's just the graphical solution of those two. Got the graph, got the answer. All right, number 12 here, 4x minus 2y equals 20 and 7x plus 5y equals 35. You know, these are in standard form, and I've stressed a little more for my students now to graph using intercepts. The way you can do it is you'd set the other guy equal to 0. So in the top equation here, when I mark it in blue, my x-intercept and my y-intercept are found by setting the other guy equal to 0. If the y-intercept is 0 comma something and the x-intercept is something comma 0, it'll be a pretty simple substitution in solving. If I substitute 0 for y in the top equation, negative 2 times 0 is 0. I'm left with the equation 4x equals 20. If I divide both sides by 4, I get x equals 5. So that's what I get, 5 comma 0. That is one of the points that is on this graph for blue. And also, the y-intercept, I substitute 0 for x, I'll get the equation negative 2y equals 20. Divide both sides by negative 2, I get y equals negative 10. So negative 0 comma negative 10 is my y-intercept. So when I plot this point down here, see, 2 points make a line, so I can draw my line through these 2 points right now. I wouldn't argue this is as accurate or precise as getting all the points, therefore I will show slope-intercept form. Let me move my picture over right here. Obviously, I'm not super important to this. It's the work that you're doing. Let me just mouse it over. There we go. So looking back, once again, these are my intercepts, and you know, I got to keep extending this probably here and get it as precise as I can just by looking at getting through those 2 points. Thankfully, these two intercepts are kind of far away. The more distant your points are, the less error you'll probably have in the long run. So let's see. I'm going to go ahead and actually write this in slope-intercept form now and see if I still hit decent points. Subtract 4x from both sides, I get negative 2y equals negative 4x plus 20. Divide everything by negative 2, I'm going to get y equals positive 2x minus 10. So in slope-intercept form here, starting from negative 10, as I do, I will rise 2 and run 1, and these will be my points right here, which look like they mostly go on that line. Rise 2, run 1, rise 2, run 1, and yeah, it looks like mine was also pretty accurate at the time. So whether I do standard form or slope-intercept form, it looks like things panned out for me pretty okay. All right, let's do this one in green, this bottom one here. And by the way, I can use standard form for both of these because I'm left with, number one, no fractions as my intercepts. If you get fractions as your intercepts, that becomes a problem. And number two, as you can tell, these intercepts are within the window range. These ones, as you might notice, will also be within the window range. The x-intercept right here, if I set y equal to 0, see if you can do this without me actually hiding the y value. But if I set this equal to 0, I get 7x equals 35. So I divide by 7 and I get x equals 5. So that's where it hits there. And oh, hey, look at that. They both hit together right there. That's nice. That's already the solution. But I got to graph them. The y-intercept, I set x equal to 0 this time. Set x equal to 0. What's the y value? When x goes away, you get 5y equals 35. Divide by 5, you get x equals 7. So 0 comma 7 is right there. I can graph between those two lines, as I stated before. Draw the line right there. And kind of decent. Let me convert it in slope-intercept form for those who are still slope-intercept form fiends and see if I got it relatively accurate. The good news is they hit at this point and not some other point floating in space. But, let's see, subtract 7x from both sides. Here I get 5y equals negative 7x plus 35. Divide everything by 5, I get y equals negative 7/5 x plus 7. Divide that by 5 as well. Now, this might look a little off-putting to you, but you have to remember that fractions when graphing is okay. We did that here. It was no problem. Here it should also be no problem. In fact, when I start from here at negative 7, or at positive 7, I go down 7 and over 5, and this is my next point that I find. And the other next point that I could find here, if I go down another 7 and over another 5, oh look, my graph wasn't so accurate because it should hit right here. So see, my line didn't actually hit accurately, which is kind of important because if I was trying to find a different point of intersection floating out somewhere, I might not have known exactly where it was. So I think using slope-intercept form there was decent for me to correct that with. Regardless, the answer still goes right here. Oh, and the point I was going to make here was fractions for slope is okay when you're graphing. fraction for slope is not okay if you're trying to solve using substitution method. We don't like fractions when we're doing things algebraically. What's this point of intersection, guys? This is 5, 0. 5, 0. There we are. Let's box both of these. Those are my answers. Solving by graphing. That's nice. All right, I have 2 more problems in full. They're kind of bulky. Number 13, we have to do several things here. First, we have to solve the system algebraically, and then we verify our solution by graphing both lines and finding the point of intersection. So we are going to solve by algebra and by graphing both. Let me start with the algebraic. Let's do substitution method here. I'm going to take the bottom equation and isolate y here by adding 2x to both sides. I get y equals 2x minus 6. Now you have 2 options on what you can do next here. I can either take this 2x minus 6 and substitute it in for y, and I think I'm going to. The other alternative, I don't know if you guys know this, I can get y by itself in the top equation as well, and then I can just set those 2 expressions equal to each other. But I'm just going to go and do that thing here. I have 3x plus 2x minus 6, that's my y, equals 9. So 3x plus 2x minus 6 equals 9. I can combine like terms here. 3x plus 2x is 5x. Add 6 over, and I get 15. On that side, divide by 5, I get x equals 3. So 3 is the x value for the solution set. We can find out what the y value is. And I'll do that by substituting in 3 for x over for this in y. Y equals 2 times 3 minus 6. That's 6 minus 6, which is, hey, 0. So we get a final solution set there that is 3, 0. And that being said, if we plotted this stuff on a graph, which we will, that's where those 2 points should intersect. Ultimately, I should be getting a final intersecting point of, well, I'm going to use green or something, color I haven't used it, of 3, 0. We'll see that we get that. Now, I could have used elimination method here as well. What's an option? I could have taken, let's rewrite these here. Well, I'll rewrite the top one, 3x plus y equals 9. And the bottom one, let's take this equation and let's multiply it all by -1. Yeah, see? Multiply it all by -1. I'll get positive 2x minus y equals a positive 6. This way the y's can eliminate when I add. So I add down the list there, and I get 5x. Whoopsie. I get 5x equals 15, and then I get x equals 3. Now when I take that 3, I'll substitute it into an equation. Let's say I didn't have this one yet. I got to substitute it into a known equation here. How about the top original one, 3x plus y equals 9? I'll get here 3 times 3, that's my x, 3x plus y equals 9. That's 9 plus y. Oh, my face is in the way. I'm sorry. Sometimes I'm not looking at what I have going on. 3 times 3 plus y equals 9. 9 plus y equals 9. And subtract 9, I get y equals 0. So you get the same answer as before, 3, 0. So there we go. That's substitution method and elimination method to get the same answer right there, which again will be the point of intersection on this graph. The last thing I got to do is graph this guy. So I have 3x plus y equals 9. And I have negative 2x plus y equals negative 6. Okay, my face is still in the way. I'm sorry. Okay, solve by graphing here. I could graph out a standard form for both of these again. Lucky, thankfully, Mr. Robinson gave you some nice, clean numbers to work with here. So in the top equation, which I'll do in purple this time, let's do it in blue. I'm going to follow along with what I was doing earlier. Blue and purple. In this top equation here, the x-intercept, set y equal to 0. I get 3x equals 9. Divide by 3, I get x equals 3. So 3, 0 there. And that's this point, which of course is the solution to the whole thing. The y-intercept, I set x equal to 0, so I get y equals 9. So I get 0, 9. So there's this point up here. And I can draw the line through those two. So that'll be right here-ish. We'll see how accurate it ends up looking in the end. But here-ish. Okay. So how do I see how accurate it is? I'm going to convert this also in a slope-intercept form, and let's see how that would look. In blue as well, I just got to subtract 3x from both sides, and I'll get y equals negative 3x plus 9. So We start at 0, 9. We go down 3 and over 1 to the right. So let's see how that would look. From 0, 9, let's go down 3 over 1, down 3 over 1, down 3 over 1. Okay, that hits. And then we keep going. Down 3 over 1. Was I pretty accurate? Down 3 over 1. It looks pretty good. Down 3 over 1. I'm not going to hate on that. I like the graph. So either you can graph out a standard form or slope-intercept form there. Personally, this one's really easy for slope-intercept form, I think. Easy enough, but standard form, no fractions. I might as well show you them. All right, x and y intercept on purple here. The x-intercept of this guy, set y equal to 0. I get negative 2x equals negative 6. Divide by negative 2. I get positive x equals positive 3. So 3, 0 is that point once again. Of course, it is our solution to the thing as well. We already know that. And then the y-intercept, you set x equal to 0. I get y equals negative 6. So 0, negative 6. And honestly, this isn't so bad either. 0, negative 6. So I draw a line through those 2 points right there. And of course, I will convert to slope-intercept form to confirm all as well. But let's draw the line through these two first. And then let's extend it. Looking good. Looking good. All right. Now let's see if in slope-intercept form, by adding 2x to both sides, I get y equals 2x minus 6. So starting from negative 6, I will rise 2, run 1. All right, and let's plot those points there. So here I can rise 2, run 1, rise 2, run 1, rise 2, run 1, rise 2, run 1. It's almost a say that 5 times fast kind of thing. Rise 2, run 1, rise 2, run 1, rise 2, run 1. See, it's going a little bit off. You see that? The points should be kind of there. And if I fall 2, run 1 to the left, it should be over here. So my line was a little off. Once again, it's probably a good thing that I have a ruler and that my points were actually on the x-axis rather than somewhere different. Because they are somewhere different, standard form can throw a little wrinkle in there if you're not quite perfectly accurate. All right, the solution set one more time. The final solution set was 3, 0. That is where those two lines intersect there. And there's that confirmation. That is verifying my solution by graphing and finding the point of intersection. So I solved using algebra with both substitution method and elimination method, and then I solved there on that last one using by graphing. Both standard form and slope-intercept form kind of both won the same. Okay, last problem here, number 14. This is called an error analysis problem right here. Camden was asked to solve the following system of equations. His work is displayed with every step numbered and detailed. Boy, Camden sure writes a lot like Mr. Robinson here, doesn't he? So here's the original equation system here. 2x minus 3y equals 14. He writes 2x minus 3y equals 14. And 4x equals 3y minus 8. 4x equals 3y minus 8. The first thing is he put everything down correctly, so that's good. Anyway, so we'll take a look at the work in a second. There are steps involved here as well, right? Step one, right here, he adds, my face is in the way here, let me shrink it. He adds the two equations to eliminate the 3y and the negative 3y. So negative 3y, positive 3y, they eliminate. And then combine all other like terms. 2x plus 4x is 6x, and 14 minus 8 is 6. He combines all like terms there. That's one step. His next step is he divides both sides by 6 to get x equals 1. His third step is he substitutes 1 in for x into the top original equation. So x is 1. We're going to take 1 and plug it into one of these two equations. He chooses the top one here and does 2 times 1 minus 3y equals 14, and 2 times 1 is 2, so 2 minus 3y equals 14. His next step is he subtracts 2 from both sides here, so 2 minus 2 is 0, 14 minus 2 there, so you're left with 3y equals 12. And then he divides both sides by 3. There should be a cancellation right there. Boop. Divides both sides by 3 to get y equals 4. 12 divided by 3 is 4. And finally, he writes his final solution as an ordered pair, 1, 4. Now, if you look at that, you might nod your head and say, yep, so all looks good. I'm with you here. Unfortunately, Camden made 2 critical errors in his work. There were 2 critical errors that were there. You might have caught on to them. You might have said, wait a minute. Identify the 2 errors by step number and describe what he did incorrectly. Okay, so let's go back to these and let's see if we can figure them out. There are only 2. Now, remember, it'll obviously change all the work that we have to do in the end, but let's still give him some of the partial credit. He did most of the other work probably correct, but 2 steps wrong. So on step 1, after copying these down, he eliminated the negative 3y with positive 3y. Now that would be a correct step, but in elimination here, you know, the whole goal, the whole thing of elimination really is that you're really adding expressions together. I should be adding 2x minus 3y, this left side with just 4x. Notice the equal sign right here? These are the only two things that should be adding together right now. This 3y has nothing to do with this negative 3y because they're on different sides of the equation. We're adding this expression with this expression. So here's the boo-boo, here's the mistake. And 14 should be adding with 3y minus 8 right there. So we're not combining things that should be combined. They're not on the same side of the equation. What I tell my students is line up x's with x if you're going to eliminate, line up x's with x's, y's with y's, constants with constants, and equal signs with equal signs. This equal sign does not line up with this equal sign, therefore we're on different sides of the equation for it. So the first error here is actually in step 1. We start off with a very critical error there. So step 1, what is the problem? The y's that were eliminated. It doesn't matter whether or not they eliminate. The problem is the ones that combined. The y's that eliminated, I'll put in parentheses because that was what we were going for, were not on the same side of the equation. What's really weird is I can always write so well when I'm not teaching here. Probably because I'm trying to talk at the same time as I type. Let me try that again without talking. You know else why? I have a microphone right in my way right here, probably. I promise I'm really good at typing, y'all. I don't know what's happening here. I think it has to do with the microphone. It limits my movement and what I can see and what I can do. All right, number 1 was actually an error there. All right, let's move along down. Number 2. Well, now listen, there's wrong work. Because they did this wrong, that means everything else number-wise will probably be wrong, unless 2 wrongs make a strange kind of right. But follow the work, okay? Still follow the work. Still be okay with kind of what's being provided here and say, okay, assuming, okay, he screwed up, but did he do what he needed to do for his work correctly the rest of the way? There's one more error somewhere. Let's see where it is. When 6x equals 6, do you divide correctly by 6 on both sides to get x equals 1? Yes. 2 looks fine. By the way, let's see. So 1, mistake. 2 is fine. Number 3, when I get this solution 1 for x, is okay that I can substitute it into one of these two equations, specifically, just maybe only the top one. Yeah, I see no problem with this. 2 times 1, 2x minus 3y equals 14. You recopy the problem down there. That's good. Multiply 2 by 1, you get 2. All right, that's good. I think that's part of step 3 still. Now, step 4, we're going to subtract 2 from both sides to get 3y equals 12. Sorry, so yeah, subtract 2. So 2 minus 2 is 0. It goes away. 14 minus 2 is 12. But was this a 3y that should have gone down here? Well, I see a negative sign right there. This happens for a lot of people. And actually, I didn't cramp the space enough to see why people often miss it. People often wouldn't miss it the way I wrote it. You got to bring this negative down with it to get negative 3y equals 12 here. And then we'll divide by negative 3 to get y equals negative 4. Of course, everything else was wrong going on top of it, but that was the other critical error there, not bringing the negative down with it to divide. So 4 is the other mistake. Dividing both sides by 3 is not considered a mistake since we're going based off what he used. So because he used a positive 3, we are dividing by positive 3 according to him. So there's nothing wrong with that. Remember, I'd give him credit for his wrong work. Here, I'd give him credit for doing that stuff correctly, if that makes sense. And then step 6 here, write final solution as an ordered pair 1, 4. X is 1, y is 4. You're supposed to write this. And he wrote it in the correct order there, so that's all good. So the other error was on number 4. And on number 4 here, what didn't he do? He didn't bring down the negative, the negative with the 3y. The negative 3y was not, the negative sign was not brought down with the 3y after subtracting 2 from both sides. Sorry about that. It's going to be kind of restricted. Looks good. Right there. All right. And that was that. 2 errors. All right. Bonus, this last thing to do, correctly and completely solve the above system of equations. Note, numbers may become very different depending on the timing and severity of Camden's errors. Remember, he made a problem in step 1. That'll probably change the numbers significantly so. So let's go ahead. I'm going to rewrite this stuff. Well, actually, I'll kind of copy and paste it here. So I take that guy. Let's copy it. Let's go ahead and paste. There we go. And I get these two, kind of blurry. But I get these two here, 2x minus 3y equals 14, 4x equals 3y minus 8. I do applaud his ability to attempt elimination, though, because if I try and use substitution, I'm going to get a fraction no matter what. So I will attempt to use elimination. But my first step I got to subtract this 3y over to the left side of the equation. 4x minus 3y equals negative 8. So now I have this equation here. Now I could try and do elimination with the y's or with the x's. This is kind of a your call thing. I'm not yet ready for either of them unless I go by subtraction, which I won't. Why don't I just to bring down the top equation with something, I'm going to go and take the top equation. I'm going to multiply it all by negative 1. If I multiply it by negative 1, I'll get a negative 2x here and plus 3y equals negative 14. And now the y's are ready to eliminate. Okay, now they're ready to eliminate. So I do negative 3y plus 3y is 0. 4x minus 2x is 2x, and negative 8 minus 14 is negative 22. Divide both sides by 2, we get x equals negative 11. And now let's go ahead and solve for y. Substitute negative 11 in for any equation of your heart's content here. Let's do this green one right here. I'm going to go ahead and take negative 2 times negative 11 plus 3y equals negative 14, and negative 2 times negative 11 is positive 22. It's negative 14 here. I got to subtract 22 from both sides, and I'll get 3y is negative 36. Divide both sides by 3, I get y equals negative 12. So my final solution here should be negative 11 comma negative 12. And yeah, I do believe that to be correct. Way different from Camden's answers, though he still got integers. And honestly, when some people get integers, they probably trust they did things right. So before I kind of sign off here, as I just passed the hour mark a little bit ago, let me really bring home what are things you can do to help yourself in problems of any need. This error analysis one is things where people could make a common mistake or where it's really easy to make that kind of mistake. First of all, you can always double check your solutions to anything by substituting in your answer into both equations to see if it works. If Camden tried to do this, and if I tried to substitute 1, 4 into both sets, I'm doing it right now as I'm looking at them, I would have gotten it correctly on the bottom equation, but it wouldn't have been correct on the top equation. So 1, 4 apparently is a solution to the bottom, but not to the top. Is that? Yeah, it looks like that is. Now, something else you could do is you could try different methods. You've seen me do that before. I've solved using elimination. I've solved using substitution in the same problem. And I've solved by graphing in the same problem as well as I've done elimination and substitution. So, but, really look back at that one problem way back near the beginning, guys, on the front page, where you have, is 3 negative 8 a solution to your system? This, if you solve the system as 3 negative 8 and you want to double check, do it like this. Substitute 3 negative 8 into the top equation, substitute 3 negative 8 into the bottom equation, and see if it works. Otherwise, like I said, you can do some of the stuff that I did here. I solved using multiple methods. Here I solved using both substitution and elimination, and I got the same answer both ways. 6 negative 9 through elimination, 6 negative 9 through substitution, things like that. So a lot of different outlets that you have there. Make sure that you know your methods because sometimes one is really better than the other. It all depends on what's going on there. It can help you. All right, so that'll be it, guys. This is Mr. Robinson. Thank you. And if you have any other questions, please ask in the comments down below. I'd love to help you out. And go ahead, take care. For some of you guys, when I don't see you again, happy holidays.